for the kind invitation, and I would like to join to you all. Congratulations and warm wishes, and congratulate one more time Nicola. In this talk I'm going to describe some recent results concerning with the very classical, I guess, problem in free boundary problems, the continuous casting problem. And another way of saying is that we're going to consider steady state Stefan problem with convection. So we're going to consider simple phase transition model, and in most places we're going to assume that this convection term given as a vector field V is going to be a constant so unit vector. Okay, so basically this is going to be the main equation that I'm going to consider, and here the interpretation is that U is a temperature at the point X, F is the guy is present here on the right hand side, it accounts for the sources or sinks, and here V is the velocity of convection. And one of the, and most importantly, you have also this function beta sitting here, and beta is the guy who's responsible for phase change. This function suffers a jump across the origin, and outside of origin there's a nice, say, linear function. And basically I should say that this vector field V in most general setting is determined from a Navier-Stokes system, because that's basically representing the velocity field of your liquid phase. However, as I said at the very start, so basically you should think of this V as some constant vector field, and in fact we'll see that it's going to be some later it's going to coincide with the direction of one of the vertical axes. Okay, so here's the motivation. Again, this is a cartoon picture which represents the kind of a clear, neat separation of two phases. And let's say you have two states. First one is the liquid, the second one is solid. And beta can be interpreted as the full energy, which is the sum of latent heat, this term here, and the heat. And latent heat is responsible for making the phase change. And here rho is obviously the density, C is the specific heat constant, and dV represents the elementary volume. Okay, so and this is the typical example of that enthalpy function. Well, in fact, you can assume that here outside of origin you have some Lipschitz graphs. I just want to keep the discussion simple, and I'm going to assume that basically this is piecewise linear function suffering a jump at the origin. And the energy conservation laws, if you use this some physical, very simple physical laws, and compute, compute explicitly what the conservation of energy gives you, then in general case you're going to get basically something like a heat equation plus this drift term, and V is basically responsible for the motion of your liquid phase. So if you don't have any motion, then you get precisely the heat equation. Well, heat equation with some elliptic operator here. Well, the Q is the flux. So depending what type of in which type of environment you consider in this problem, you may have different forms for this Q. But again, just because the simplest case, you can assume that Q is a multiple of the gradient. In that case, you get the heat equation. Okay, so here's the outline of the talk. I hope that I will be able to cover pretty much everything which is listed here, and I'll just discuss some known results for this problem, again in steady state case, then discuss the up to the boundary for weak solutions, and then optimal local regularity for weak solutions, and then make a bridge between weak solutions and viscosity solutions. And that will allow us to apply the well-known theory for regularity of free boundaries, solutions of free boundary problems in viscosity sense in this case, and obtain some regularity results. Something like if you have Lipschitz, then Lipschitz implies C1 alpha. All right, so here's the the domain that I'm going to consider is basically a cylindrical domain of height L. This base domain omega is assumed to be sufficiently smooth, say you take it to be Lipschitz, and this is going to be the standard notation that I'm going to pursue throughout this talk. X stands for the kind of horizontal coordinate, and Z stands for the vertical coordinate. And du is the usual gradient, and this particular choice of domain is motivated from physical applications, because this continuous casting problems is used in production of ingots. And when you have some molten metal and you want to kind of cool it off, then the metal is extracted with constant velocity, and that velocity is going to be the convection. And in fact, this direction is going to be, this vertical direction is going to be the direction of extraction, and that's why. So you think of just pure from point of view in terms of applications, you're basically assuming that this is representing the kind of a chunk of that flow of molten metal, and because of in production it's easier to consider cylindrical kind of domains. That's why here I'm going to consider this particular choice of domain. And first I want to mention the existence result. So if you impose some boundary condition, say G, and then you formulate this problem in weak sense, and then you're basically seeking a pair of functions, two functions, u and eta. Your u is the temperature and eta is enthalpy. And then here's the weak formulation of this equation. And then Rodriguez, I guess, was the first to give a fairly general existence result for these problems. So he assumed that omega, the base domain, is Lipschitz, V is L2, your source is also L2, and G is Lipschitz continuous. Then there exists, I guess, there exists a weak solution to this problem. And another property that these functions, these solutions enjoy, is the comparison principle. And in the nutshell, if you just think of the standard comparison principle, say for Laplace operator, you don't change much here in the formulation of this comparison principle, except that you're assuming this extra condition for your two functions to be compared. And this is actually called a sufficient condition for stability. This was introduced by Kamenometskaya, and basically it is shown that if this condition is not satisfied, then this comparison principle doesn't hold. So there's a condition that we should impose. In fact, just choosing some particular boundary data, nice boundary data, will ensure that this sufficient condition. This sufficient condition for stability will be satisfied. Say you take positive. Say that on the top of your cylinder, your boundary data is some positive constant. That will do the trick. And for that particular boundary condition, this condition would be satisfied. Okay, and clearly from this comparison principle, and as I said, if we just consider this, just impose these conditions on our boundary data set on the top or on the bottom, then that sufficient condition for stability will be satisfied, and you will get uniqueness. Okay, so if you combine Rodriguez theorem and comparison theorem, you will get that there exists unique weak solution on the fairly general conditions on the data. Right, now I'm going to improve slightly the known continuity estimates for this problem. It is known that the solution that Rodriguez obtained is going to be at least locally Hilbert continuous. And so first step here is to obtain log Lipschitz continuity up to the boundary. Again, I'm going to consider particular choice of boundary data just to keep the argument simple. So I'm going to assume that on the top and the bottom of my cylinder I have constants, a positive constant on the top, a negative constant at the bottom, and G is now the function that lives only on the cylindrical portion of the fixed boundary. And I'm going to assume that G is, say, Lipschitz, okay? And clearly, I need some compatibility conditions that, G agrees with these two constants on the top and on the bottom. And then, for this case, I will obtain up to the boundary log Lipschitz continuity for my solution. And moreover, if I assume that that G, the boundary condition that lives on the cylindrical portion of fixed boundary, is strictly monotone in z direction, then in fact my solution will inherit that monotonicity, and I can show that the free boundary is log Lipschitz continuous. You can regard this free boundary as a graph over the base, and that graph is going to be exactly log Lipschitz continuous. In fact, you can slightly strengthen this statement and say that your free boundary is going to inherit exactly the same regularity that your U has. Okay, so imagine if you had, say, somehow you managed to get Lipschitz regularity up to the boundary for your weak solution, then your free boundary in this case would be Lipschitz continuous graph. However, we'll see that we cannot hope that that the weak solution is Lipschitz up to the fixed boundary. Okay, and the proof of this this theorem is, the first part regarding the log Lipschitz regularity is fairly standard. One uses very standard potential theoretic estimate. So you divide your cylindrical domain into kind of three parts. So this is the first part that corresponds to bottom and the top, and then the lateral boundary, and this is the second part, and then finally the interior. And for instance, for part one, you can use the reflection argument and then apply some well-known estimates for continuity for log Lipschitz to retrieve the log Lipschitz continuity near this piece of the fixed boundary. And similarly, that applies also to the bottom. And here, near the lateral boundary, you use some very classical potential estimates. And finally, in the interior, if you kind of away from the fixed boundary, some fixed portion, then you can apply standard, say, the Georgi type. Not Georgi type. Green representation, and again obtain the log Lipschitz regularity for this case. So the first part is kind of more or less standard. As for the second part, then the proof of the second part uses domain shift argument, and the idea is that you just take your U and you compare it to, say, Ux plus some H times E. So let's say E is a unit vector and H is the size of the shift. So I think that this is the original domain. Then you just shift it by some vector H times E, and then you try to compare these two functions in the intersection of the domain and its shift. So in this direction, in the z direction, you're going to have strict monotonicity, and the size of the monotonicity will be given by this constant here, C0. Okay, but however, if you're moving in horizontal direction, right, you lose the monotonicity, and therefore, So if you try to compensate between the vertical and horizontal movement using this inequality, then in fact you can get that this inequality is satisfied. Okay? In particular, if you just move only in z direction, so there is no movement in horizontal direction, then you're going to get the usual monotonicity. Unfortunately, you can't claim that this monotonicity is strict. Okay, you can just say that it is monotone, but it's not clear whether this monotonicity. I mean, you can kind of estimate the size of monotonicity as it is done here. And also another important thing here is that this constant, the monotonicity constant C0, appears, actually the reciprocal of this constant appears here. And clearly, if you lose the strict monotonicity, in other words, your function gets closer and closer to just a non-decreasing function, then this estimate violates. Okay, therefore this assumption is important in order to obtain the monotonicity of U. Okay, and then after having this monotonicity, you can actually consider these two semi-continuous functions, h plus and h minus. And here I have a bit weird picture. So in this case, you don't have neat, clear separation of phases. You might have this so-called Mashi region. And Mashi region means that you have basically points where you have neither ice nor water. So your latent heat is not enough to make the change of phase. But if you have the monotonicity condition on your G, that actually forces these two guys, H plus and H minus, to coincide. Okay? I mean, it's now they coincide, and in fact, one can show that that function, let's say H plus or H minus, it's going to be log Lipschitz continuous, and the proof is fairly elementary. So you just increase this point by size epsilon, and sigma here stands for the modulus of continuity of our function. That's log Lipschitz continuity. Log Lipschitz modulus of continuity. So if you decrease that by h, right, and use the monotonicity, and you take your z1 to be this number, then you have this inequality thanks to monotonicity. And since you are epsilon above your free boundary, then this is going to be positive, which forces your z2, right, be above of the level 2. And therefore, you will have that h plus x2 should be strictly less than z2, and then you just send your epsilon to 0, interchange x1 with x2, and you get log Lipschitz continuity. In fact, I had written sigma here just to emphasize the fact that it's not really important what's the modulus of continuity of U. The important thing is that your free boundary is going to inherit exactly the same modulus of continuity. But there's a global result. Okay, so and the hope is that perhaps if you go inside of your domain, you will get something better than log Lipschitz. And the hope is that you will get Lipschitz regularity. And again, some motivation why you hope to get Lipschitz regularity and why Lipschitz regularity is going to be optimal. Well, it's because of this free boundary condition, or some sort of a jump condition for the normals. And it's easy to verify this condition, at least formally, by doing some clever integration. If you kind of move inside of your positivity set by size epsilon, and do the same thing with the negativity set by size, say, minus delta, and then you just integrate this equation in the corresponding domains, and then finally send epsilon and delta to 0, you will get this. Okay, and which is kind of a weak formulation of this condition. And of course, if your free boundary is, say, C1 alpha, then this condition will be satisfied in classical sense. leaving no room for the hope of having better regularity than Lipschitz. Okay, so therefore this condition says that, well, the best regularity that you can hope for is Lipschitz continuity. Okay, and for Lipschitz continuity, I'm going to consider two cases separately. First one is the one-phase case, when you could think of that in physical terms, it means that your ice has constant temperature 0. Okay, and for this case, so assume that U is some bounded solution, local solution of our equation. I mean, this is a H1 function, obviously, and assume that your convection is some L infinity vector field. Then locally this U is going to be Lipschitz continuous. And the argument is based on the so-called dyadic scaling argument. In other words, you're trying to show linear growth away from the free boundary in some discrete form. So obviously if you have this inequality, then that gives you linear growth away from free boundary. And if you want to prove this, then you argue towards a contradiction. Assume that, well, you have some sequence of integers going to plus infinity, family of big solutions, bounded, and also sequence of points on free boundary, such that this inequality fails. You have the opposite inequality. Okay, and in order to arrive at contradiction, we use this scaling. So you basically scale with respect to kind of a half ball. All right, and you just scale it by a minus k power of 2, but divide by the supremum of U over half of this size of scaling. And then obviously, just from definition, you will get this condition, which gives you non-degeneracy. Obviously, you get that at the origin. Now, all these functions, all these Vj's are defined in a unit ball centered at the origin. All these scaled functions vanish at the origin. And finally, you'll get this uniform estimate for Vj's. And that's, again, if you just divide both sides of this inequality by this supremum over 2 to the power minus kj minus 1, then if you just move this to the left-hand side, you get exactly this inequality here. Okay, so this gives you a uniform L infinity bound. And then, so what happens to the equation? Again, if you do the direct computation, it shows that this is the equation that your Vj is going to satisfy. And now you have slightly modified vector field Fj, which is now kind of a modified convection. And then you can actually estimate very roughly this Fj, and you will see that this is converging to 0 due to the fact that, so basically here, so this is bounded. So if you just move this to the left-hand side, then that will give you that 2 to the power minus kj divided by this is less than 1 over j, right? And that's exactly why you get this 1 over j here. And this gives us that in the limit, I mean, if we manage to obtain some good compactness for this family of functions Vj in, say, H1, the limiting function is going to be harmonic. As for the, say, H1 estimate in the ball that contains the half ball, because remember that we have non-degeneracy in the half ball, so this is the non-degeneracy, and we don't want to lose it. So therefore, if you apply the Kacher-Pauli, you will get L to estimate for the gradients in slightly smaller ball, but it still contains the half ball. And then from the Georgi, you will also get continuity. Anyway, if you just send this J to plus infinity and use very customary compactness argument, then you will end up with a harmonic function which is 0 at the origin, non-degenerate, the supremum is 1/2 in a half ball, and obviously that function also vanishes at the origin, which forces that function to be identically 0, which is in contradiction with this non-degeneracy assumption here. And that sort of gives you the linear growth for one-phase problem. All right, now what happens if we consider the two-phase problem? In two-phase problem, we have to use some monotonicity formula techniques, and one of the standard tools in two-phase problem to treat two-phase problems and to obtain some regularity is the Alt-Caffarelli-Friedman monotonicity formula. And it basically says that if you give me two non-negative subharmonic functions with disjoint supports vanishing at the origin, these two functions are continuous, then this guy, this phi, is going to be monotone non-decreasing function of R. Right? And I guess it's worth to mention a particular case of this formula when the dimension is 2. So if the dimension is 2, then this Newtonian potential disappears, right? And you get a multiplication of pure Dirichlet energies normalized by some power of R. Well, to be more precise, it's -4, and then say U1 squared. Okay, and if you try to, so this is our phi. So if you take the logarithm of this phi and compute its logarithmic derivative, then you're going to end up with something which is related to the lowest eigenvalues of Laplace-Beltrami operator on a circle. And more precisely, you're going to face the following situation that, say, you have two complementary cones, say gamma 1 and gamma 2. Again, this is the picture in R2. Okay, then so the fact that this guy has non-negative derivative is equivalent to showing that alpha 1 plus alpha 2 is bigger than or equal than 2, and this alpha 1 and alpha 2 are I don't want to cheat, I guess they are exactly the smallest eigenvalues of Laplace-Beltrami operator. In fact, you can see that this is exactly 2 if you have half circles. All right, so this is the meaning of this monotonicity formula. In fact, you can compute these smallest eigenfunctions and eigenvalues explicitly, so it's going to be something like some sine functions depending on the aperture here, alpha. All right, and in high dimensions, well, the situation is much more complicated. One needs to use some convexity property of eigenvalues to conclude that this is a non-negative, non-decreasing function of R. And actually, there's one more thing to say about this phi, is when your phi is constant for, let's say, any R between 0 and 1, then the supports of these two functions are going to be half spheres. So they don't need to be exactly, they don't need to be homothetic to each other. But for each level R that you give me, the corresponding trace is going to consist of two complementary half spheres. All right? So this is a very important property of for the property of this functional phi. And then there is a generalization which is due to Caffarelli-Jefferson and Koenig. So if you consider, instead of subharmonic functions, solutions to this differential inequality, so Laplacian is bounded below by some constant, say -1, then this phi is not monotone anymore. However, it's bounded. And again, that's enough to obtain Lipschitz regularity for two-phase problems, even if you have solutions to this differential inequality. Okay. All right. Now, the task is to reformulate our problem so that we can apply monotonicity formulas and conclude the linear growth. So to do that, I'm going to use a technical trick. I'm just going to well, now from now on, I'm assuming that V is a constant vector field. It's basically the unit direction of vertical axis. The sources are 0, so this is the equation that I get. And then if I multiply my solution u by this exponential function, then a direct computation shows that w is going to satisfy this equation. And in fact, the positive negative parts are going to satisfy this nice equation. So now the trick is that here in this modified equation, you get rid of the partial z, the partial derivative of the u. Right? So now this becomes a semilinear equation. And clearly, if your u is non-negative, this is also non-negative, w is non-negative. And clearly, if your w is bounded, then you'll get this inequality for your w. For Laplacian of w, sorry. All right. So then, for this modified functions, you can show that if if the convection is constant and the sources are 0, then you have local Lipschitz regularity for your weak solutions. And again, the proof is very classical. It's based on argument from a paper by Altke, Frelly, and Friedman, Transactions of MS. And first thing is that you estimate the Laplacian of your w is that modified function, u times the exponential, and you get this estimate for Laplacian. And this is due to the fact that our beta had a jump across the origin, and very loosely speaking, the Laplacian of u is something like delta function on gamma. In other words, again, this is very, very rough. You have that u is something like, say, r, and say the r x0. Gradient of u is something like 1, and then the Laplacian of u is something like 1 over r. Because it's kind of the scaling kind of properties of, well, of course, strictly speaking, this is wrong, but this is kind of the meaning of this inequality here says that if you just take the mean value integral here, then the Laplacian behaves something like 1 over r. Okay. And this just follows from standard potential estimates. No, sorry, this one actually follows from divergence theorem. You just just integrate the equation. Here's your equation. So just integrate this, then you will get this. And then using that estimate for the Laplacian, you can get this coherence estimate. This is one of the most important estimates, which says that basically your u plus and u minus you have pretty much in the same way. If one of them goes to, say, if you consider this difference, then this is it behaves something like rho. In other words, if I just now divide both sides by rho, then this becomes a bounded quantity. In other words, if say if u plus doesn't have linear growth and this integral goes to plus infinity, then so does u minus. In other words, both guys should go to plus infinity simultaneously. All right, and therefore now if you think of the monotonicity formula, if monotonicity formula enters to the game, and you also know that the product of these two guys remains bounded, that will give you the uniform bound for both of these mean integrals, giving you linear growth from both sides of the free boundary. All right, so there's a crucial estimate, and to obtain this estimate, you use some very standard argument involving potential analysis, namely Green function. You just consider the Green representation of your W, and then at the origin, the point where x0 that belongs to your free boundary, you get equality of these two integrals because at that point your W vanishes. And then you just do some very standard elementary computation, use your estimates for the Laplacian of W, and that gives you the coherence estimates for U plus and U minus. All right. And finally, we also want this. We also want to show that these modified functions, if you just multiply U plus and U minus by these exponential functions, they satisfy that differential inequality. The Laplacian is bounded by below by some constant, you can't really use your differential equation in a ball centered at the free boundary, because, as I said, the Laplacian behaves something like a Dirac across the free boundary. So you can't immediately conclude that the functions are satisfying that differential inequality. But all you have to do is just to add some quadratic function to this W plus and W minus for some suitable constant C, and then check that this new function W plus this quadratic function is locally subharmonic. In other words, for each point that you give me, I can find a neighborhood, and in that neighborhood your function is subharmonic. Since subharmonicity local implies global, you will get subharmonicity in entire domain. Okay, and this is the argument. Therefore, the conclusion is that the conditions on the conditions of monotonicity theorem here, M1 and also M2 are satisfied, and that gives you the following estimate, that this mean value integral 1 over rho this to the power 4 is bounded by some constant and then phi 1. Okay, and just combining these two inequalities, you'll conclude that both mean integrals for U plus and U minus are bounded if you stay uniformly away from the fixed boundary, and therefore you get linear growth, which implies the Lipschitz regularity. Okay, so this is the Lipschitz local Lipschitz regularity of the solution. Now, what about the regularity of the free boundary? Well, in general, one can separate the regularity results for free boundary problems into two groups. First one are also called weak regularity results, and then also full regularity results. So the weak regularity result means that you basically get something like partial regularity. In other words, you have part of your free boundary where it's smooth, and the complement is small, and this smooth, by smooth I mean that each of these pieces is C1, let's say smooth. So this is the rectifiability kind of property of the free boundary. And to show this, actually one has to link this U to a classical obstacle problem via Baiocchi's transformation. That we'll discuss it later. So that's a way to obtain the non-degeneracy for U plus for free, because you know that for obstacle problem the solution is not degenerate, and then you do some tricks and retrieve linear non-degeneracy for U plus. And as for the proof of this statement of partial regularity, it's enough to show that your free boundary is locally a set of finite perimeter, and that can be done by some very standard covering theorem using, for instance, Bezikovich type covering theorem. So you take a ball Bx, and then you consider this measure, say Laplacian of U, and then if you know that the following estimate holds true, say this is bounded by below by some constant, uniform constant, universal constant, and say Rn minus 1. Okay, and this is true for any Brx which is in some compact set in our cylindrical domain CL, then if you use, say, if you cover your free boundary by such balls and use Bezikovich type covering argument, you can estimate the preimage of Hausdorff preimage of this free boundary. So you'll get that the sum of, so C here, Ri n minus 1, and you sum with respect to all i's. I is the index that represents, so sort of recognizes the representatives of the covering. So this is going to be some union of, well, actually not a union, but sum of slightly bigger balls, say B5 Rix, and i's from, again, you just sum this up with respect to all i's, and then you can choose these balls in such a way that you have finitely many overlappings. And here you have the Laplacian of u, so this is going to be bounded by C, and then some neighborhood of this k, say k epsilon neighborhood of the Laplace of u, right? And if your Laplace of u is Radon measure, and it is going to be Radon measure because of the discussion above, then you get an estimate for n minus one-dimensional Hausdorff pre-measure, meaning that this is done on the assumption that your Ri's are sufficiently small. And then you send your delta to 0, and you conclude that the n minus one-dimensional Hausdorff measure of the free boundary is finite. That gives you that the set is of, it's a Cacciapoli set, and then you get this partial regularity result. And here, this was the crucial estimate, that you can estimate this measure by below. There's some power, right power of R, and this is actually thanks to non-degeneracy of u plus. Well, u plus u is the same thing because we're considering the one-phase problem. Okay. And now, what about the full regularity results? Then my aim is to show that Wick solution is also viscosity solution, and then apply the theory that Lewis has developed, the Harnack inequality approach, and show that, for instance, if you give me Lipschitz free boundary, then it's going to be C1 alpha, right? Therefore, the primary issue is now to show that the Wick solution, H1 solution that I obtained, which turns out to be locally Lipschitz continuous, is also a viscosity solution. And then here is the definition of viscosity subsolution. Well, the first condition says that my u is continuous in basically in the closure of positivity set and negativity set relative to this domain D. Sorry, CK it's not continuous, and it's going to satisfy this differential equation. So from now on, I'm assuming that the slope of that linear functions that my beta is composed of are 1. So just normalize and take that A to be 1. So second condition says that U is a subsolution of this inequality. And third condition says that, well, the gradient of U plus is positive, which allows me to apply the inverse function theorem and represent my gamma as a CK surface. And you also have, this is a crucial inequality, that this inequality must be satisfied, where this G is basically the free boundary condition. And E is the unit interior normal to gamma. The idea is that, I mean, the definition of this viscosity subsolution is tailored in such a way that you cannot have viscosity subsolution touching a solution from below. Okay, because this condition, if you apply Hopf inequality, this will prevent subsolution, touching solution from below. And this is a smooth viscosity subsolution. Okay, smooth means that it's at least CK. And so now few words about this G that represents the free boundary condition. It should be elliptic in the following sense, that if you just consider this G to be a function of A and B, which represent the kind of the normal derivatives of U plus and U minus, then it should be increasing in A and decreasing in B. And recalling our free boundary condition, which is formally written in this form, you see that it's basically a linear function in A and B, right? Therefore, clearly, it's increasing in A and decreasing in B, right? Therefore, in the sense that's what Lewis defined. So, in that sense, this G representing this free boundary condition for continuous casting problem turns out to be an elliptic free boundary relation. So we can apply the Harnack inequality approach. And finally, the definition of viscosity solutions. This is my favorite part of the slides because it's very long, but I'll give you some geometric explanation of these two cases that I will be considering. So first one says that, well, I'm considering this a solution to this problem, semi-linear equation, and the reason why I'm considering the semi-linear equation is because if you consider W, which is this U times e to minus dA over 2, which is, so my A is 1, so this is this function. So for this modified function, it's easy to see that this is the equation that's going to be satisfied in positivity and negativity sets. Okay, and then now I want to reformulate the free boundary condition in weak sense, because in general I don't know whether my free boundary is CK regular, right? And therefore I'm just going to reformulate that condition using touching balls from either side of the free boundary. And the first one says that, okay, assume that you have a touching ball at x0 and that ball is inside of the positivity set. Then you should have this inequality, and then also in the complement you will have this inequality with some constants A and B, and moreover your A and B must satisfy this relation. And now the second case, when your ball is inside of negativity set, then you'll have this inequality plus the inequality satisfied in the complement, and then you must have this inequality, the free boundary relation for the constants A and B, which kind of represent the linear growth rates in these asymptotic expansions. Now the meaning of this, I mean, why these inequalities, these asymptotic expansions must be true, right? Why I'm assuming this? Well, it's because that you can in fact prove that if you have a domain, say this is domain omega, and you have a solution of the semi-linear equation, your U is non-negative, and you have a ball touching this, so this is the boundary of omega. Okay, it's fairly general theorem. Then your U either grows faster than any linear function, or you're going to have this estimate. So in our case, because we know that our solution is Lipschitz, the first alternative is eliminated, so you're going to have only this asymptotic expansion. And similarly, if you have a ball now on the other side here, you're going to have a reversed inequality. And this is basically due to the fact that ellipticity is propagating asymptotically, at least in this half space. And therefore, here the first one says that you cannot have your function growing asymptotically slower than linear. And A basically gives you the rate of this linear growth. Okay? And the proof, again, it's a standard proof. You use the capacitory potential. So you take a function which is 1 here in the half ball, on the boundary of half ball, and 0 on the boundary of bigger ball. And you're considering A to be the supremum of all gammas for all m's for which this inequality holds true. You show that the set is not empty because your solution is Lipschitz continuous. And therefore, I mean, if you do this argument carefully, then that A, the supremum that appears here, is going to be exactly the A in this in this inequality. Moreover, you're going to have equality in any non-tangential region. And non-tangential means that we're kind of approaching to this point within a cone. And in any such cone, you're going to have actually equality. Right, then, just want to recall the original theorem of Lewis and its generalization by Mikhail Feldman. So if U is the Viscosity solution and of the free boundary problem, and let's say your free boundary is Lipschitz, then the free boundary is in fact C1 alpha continuous, where alpha is some positive number between 0 and 1. So Lewis proved that for Laplacian, and Feldman generalized that for fully nonlinear equations depending, or kind of a semi-linear, something like he was allowing dependence on U as well, and this is crucial for us because we are considering the semi-linear equations. And now, finally, the theorem that relates to Wick and viscosity solutions. So if U plus is non-degenerate, so this is the, what does it mean? Then the Wick solution is going to be also a viscosity solution. As you can see here, this is proved under this non-degeneracy condition. I just want to now talk a little bit about this non-degeneracy. And in fact, if this is not true, then the proof that I have wouldn't work. So this is a crucial condition that guarantees that Wick solution is also viscosity solutions. And but actually, one can justify why your U plus is going to be non-degenerate. And the justification comes from a relation that I already mentioned between the continuous casting problem and the obstacle problem. So if you consider this equation, so again, let's assume that f is the source term. Let's spare this function. Don't assume that it's 0. And then you integrate this equation from 0 to z. Basically, you're integrating it in vertical direction. And after some elementary simplifications, you just see that the right-hand side is a linear function in u plus a multiple of characteristic function where u is positive. So this looks pretty much like an obstacle problem, except the fact that here you have u and here you have w. So w is going to be the Biocchi transformation, which is basically an integration of your u in vertical direction. Okay? So therefore, I mean, this is not really the obstacle problem, because in obstacle problem you expect same function to appear on right-hand side and left-hand side. But now if you recall the monotonicity of our Wick solution, then perhaps these two sets do not agree, but at least you have this inclusion. Okay? And that inclusion allows you to show that your W, the Biocchi transformation, is actually enjoying this non-degeneracy. And clearly, if so, L is the size of the jump that is manifesting here on the right-hand side of the equation. And clearly, if your R is sufficiently small, you get the linear non-degeneracy for your U plus. Okay. And M here is some constant that depends on L infinity norm of the gradient, the Lipschitz norm of the gradient. And the and the proof is again very standard. It's just based on the comparison principle of function and mean, the quadratic kind of dilation of the function, the standard argument that is used in obstacle problem to obtain the non-degeneracy. So therefore, this non-degeneracy assumption here actually is not something really strong that we are imposing. In fact, this is always true for a weak solution which is monotone in z direction. Therefore, the weak solution is viscosity. You apply Caffarelli's theory and get that Lipschitz free boundary is going to be C1 alpha. I guess I'll stop here, and I will again congratulate you on your birthday, and thanks very much for your attention.
One quick question. I was wondering about this mushy region, because first it was completely separated. We have a real mushy region. Does it happen that in general in application?
In general, yes, you might have mushy region.
But can it happen that two, let's say, let's call it free boundary, they touch but not completely?
Yes, it might happen. I mean, if your lateral boundary condition G is not monotone, there are some examples constructed by Nocetto. He has some numerical simulations.
So there can be a mushy region.
Yeah, something like.
And part of the boundaries are touching completely.
I mean, I don't know what you mean completely, but you can have something like this.
Oh, yeah. Well, I mean, it's a piece of.
Yeah, perhaps you could sort of get a little bit more than a point here, but yeah. I mean, there are examples of boundary data G
that creates a third version of free boundary. It's sort of three phases.
Kind of, yes. Or three regions, let's put it that way, yeah.
Mushy region corresponds when you have sort of a slash.
Mushy region, I
A
think
mix of water and ice.
Water and ice, so it's like put it zero temperature.
So it's a zero temperature, but not enough heat
Yeah.
to melt the ice. Yeah.
So you have minus, plus, and zero, and all of them
Somewhere, yeah,
positive volume.
most of the times that's inherited from the initial.
Yeah.
Depending on the problem, in general, it will not appear spontaneously. It's more like initially was there, it's going to stay for a while.
Okay, so thank you.
Thanks.